the show has begun. Welcome, Zoomers, back to the basement. It is very warm outside today. I don't know. I went running earlier and it felt really hot, so it's like summer is still going strong here, even though we're well into the fall. We have today some confirmatory factor analysis stuff to talk about. I am working on retooling the handout that goes with this unit to add R code, and it is not done yet. So we will start that at some point next week as soon as I can get that done. But the good news is that I've learned a lot better how to use Lavon and all of its various functions. So I love learning. That's why we're in this profession, right? Learning is fun. So we have, let's see here, lecture 4 is what we're talking about here. I am not going to share screen yet, so I can ask you my customary review question, although the Zoomers can see the screen that I'm on, or the YouTubers, I should say, that's being recorded. What do you remember from last time? And as usual, I will take letters, words, gestures, chat window, voices, symbols, emoji poops, whatever you got.
One key difference between EFA and CFA is that CFA can be disconfirmed.
Yes, CFA is a disconfirmable framework in which you can put forth your idea as to how these items are related. Basically, what are they measuring, and that then in turn predicts the type of relationship, and you can see the extent to which you're right or wrong. Yes. Comment in the chat: ovals and boxes and possibly triangles. Oh my. Which one is for real things? Boxes, yes, and I will take squares or rectangles. I don't care. The size of the boxes can be adjusted for the name of whatever goes in the box. That part doesn't matter. That means that not real things go in, yes, ovals or circles. Again, shape doesn't quite matter. Yeah, and what are the stupid triangles for? Yeah, intercepts. The stupid triangle is the column of ones that would normally have to multiply the fixed intercept in order for it to be introduced into the model. So if you think of this in like a matrix formulation, that's the role of the stupid triangle. I call it the stupid triangle because to me, like, every box has a mean associated with it, and I don't need a special path to indicate that. So that part of the model doesn't actually convey the structure that you're putting on. Like, all boxes have means already, just like all boxes have some kind of variance already. It's the question about the relationships among the boxes that you're putting the latent variables in for. That's the part that the diagram is intended to convey. So I call it the stupid triangle because it just clutters up the diagram with things that are irrelevant to the hypothesis that you're testing. What are the types of item parameters in a CFA model? There are 3 things typically estimated for each item. 3 types of things, I should say. Okay, got a couple different answers. So one answer was means, variances, and covariances. Those are the pieces of information with which the item parameters are going to be estimated. So it's like the other side of the equation. What is an item parameter? There's 3 kinds. We got intercepts is one. Yep. So every item has an expected value based on all the factor scores that predict it being 0. We also have slopes, and the fancy word that goes with slope. Yeah, factor loadings. Yes. So a slope factor loading, the symbol for it is lambda. So we have 1 loading per factor. So every factor that an item measures has a loading attached to it, potentially, that goes with that factor. And then last but not least, the tricky one, E. Now, is E a parameter per se?
Yeah, it's person something interactions.
Person by item interaction is how I would think about that, yes.
Okay.
Yeah, so it's the variance of the E's for that item specifically. That's the parameter. Not each individual E, but the variance across people of the E's for that item. And typically what happens in these models is that each item gets its own intercept, no questions asked. each item gets its own error variance, no questions asked. The questions really are about the loadings. If it's only one factor, then that's each item's supposed to measure it. But if there's more than one factor, then you have to decide for each item, does it measure one factor, the other, or both at the same time. So multiple loadings potentially, but only one error variance and one intercept. What about the factors? Are those people quantities or item quantities? Yeah, people. F is for people. So each person for each latent factor has, in theory, one factor score. We don't know what it is, and we don't actually need to. But the theory is that I have this amount of ability, or this tendency, or this capacity, or this attitude, or this behavior, or like whatever the thing is that we're measuring, this tendency. And that tendency then dictates how I would answer all the questions. That's the underlying way that this works. So F has a subscript of S because it's a subject-specific quantity. And as we will talk about in more detail later, F is assumed normal, multivariate normal in models that have more than one F. So one of the consequences of that simplification or that assumption is that we don't need the Fs for all the people. They're not even part of the output unless you specifically ask for them to be predicted. Because all we need, given that it's multivariate normal, is the means, variances, and covariances of the F, and those are sufficient statistics to work with in terms of computing likelihood and getting all the model parameters. So we don't need the Fs. They are latent. They are random variables. Random effects is another way to say that for each person. We can predict them, but we will have to keep in mind that each estimate of someone's F is only that. It's actually a measure of central tendency of a distribution that has error to it. And how good the model is dictates then how good the reliability is, dictates the standard error. So if the model fits, then you can talk about reliability, generate standard errors, generate confidence intervals around scores, and that kind of thing, just like regular. All right. Okay, here's a question, since you can't see the answers. Which way do the arrows go in the diagram? Do they go into the circles or out of the circles? Out, yes. So the factor is the predictor, and error technically is a predictor too. So the stuff on the right side of the equation, the arrow goes out of. The stuff on the left side of the equation, the arrow goes into. Good. I think that's all the big part. How do we know if an item is good? Let me ask one more and then I'll answer the question. What makes for a good item according to this framework? Yeah, higher loading and bigger slope. Do intercepts matter in terms of how good an item is? Not right now. They'll matter in like a month, but not right now. The reason they don't matter, the slope is linear. So it's a good item regardless of where you are on the trait if it's a strong slope. That's the assumption we're making. It's a strong assumption, probably wrong, but that's what the model says. Had a question about terminology of endogenous and exogenous. Yes, so endogenous means outcome. Exogenous generally means predictor. That distinction gets a little squishy when it comes to what happens with missing data and likelihoods and stuff, but I can say that all of the item responses are endogenous definitely because they are being predicted and they're part of the likelihood. The latent factor is not really a real thing, but it's viewed as a predictor in this case. Eventually, when we get into higher order models, you can have latent variables that are predicted by other stuff, and then they would be considered endogenous, even though they in turn predict item responses. All right. Anything else you can think of I'm forgetting? Or other questions that are coming to mind as we talk about this stuff?
Lisa, I have one.
Yeah.
I know that we are assuming that the latent trait is a continuous variable, but do we have to assume some kind of distribution for that latent trait?
Yes, we do. It's normal.
For CFA models or for every model with a continuous latent trait variable?
Every model in this semester.
Great.
So when people talk about CFA, IFA, IRT, and SEM, they are almost always talking about continuous latent variables assumed to be multivariate normal. It is technically possible to make some other choice, depending on the software. For instance, diagnostic classification models, the latent variables are categorical. They are viewed as classes or states rather than continua. And there may be hybrids also possible, where some variables are classes and states and others are continuous. But for our purposes this semester, and certainly these models, the factor scores are continuous and they're supposed to be normally distributed. Now, in reality, if we were to output a distribution of the predicted factor scores for a sample, and you will see this, they're not going to be normal in most cases. Because the kinds of items that you have by which to try and figure out what each person's factor score would be are going to govern that distribution. So like if you have a data set where the items are things that are infrequently observed, so like you're studying some rare type of phenomenon where most of the people are going to say nope, don't do it, never happened, etc., you're going to get a pile on one end of the distribution of factor scores where there's a giant floor effect. It's not going to be normal, because that is going to be the people who said no to everything. And the only reason that you can have a score at all is the assumption of underlying normality. But it's not going to look like a symmetric distribution because the information in the items isn't going to permit that. So you will see floor effects, ceiling effects, and weird sort of bumpiness in these distributions because of the item responses and not having enough to fully fill out like what the factor score distribution would be. Questions? We still assume normality of F even if the responses are not normally distributed. Yes, we do. So if the responses are normally distributed, that's what CFA is for. If the responses are some other kind of distribution, then we need to take this model and add some stuff to it. So if we have binary or categorical responses, for instance, we're going to throw on a link function that's either a logit or a probit and switch out the E distribution from something that's normal into Bernoulli or multinomial. If we had some kind of item response that's a count or something, then we would switch out the link function to predict the log of the count, and then we would switch out the residual distribution to like Poisson or negative binomial or something like that. So this is sort of the building blocks of the model, which is why we're doing it first, but we're going to have to customize it to predict anything that has boundaries or that isn't really continuous, which is most item response formats. Doing it this way is mathematically easier, simpler, and faster, and it came first, so that's why we're starting there. But yes, F is always normal. Okay. Anything else? All right, then I will share screen so we can start talking about some new stuff. And make sure I'm recording, as usual. Yes, indeed. Okay, so we were talking about different types of solutions, and we started talking about at the very end how these models actually predict or try to recreate means, variances, and covariances. So starting then, let's see here. Let's go this one. Come on. There we go. Slide 12 in lecture 4. That's where I am. Yeah. A little bit of a lag. Not unlike the uncomfortable silence that sometimes happens in class anyway, but this is just my computer not wanting to talk to me. It happens sometimes. So we looked at this slide last time. This is an unpacking of the more general equation to describe what happens to each particular item in this little hypothetical example. So I've got 6 items, 3 are thought to measure the first factor, 3 are thought to measure the second factor. So if I write out what the model is saying goes into each of these responses, each item gets 1 intercept. That's always true regardless of how many factors you have. And then each factor has a potential loading in front of it that conveys how strongly the factor predicts that item response, where more is better, 0 means they're not related, and negative means something went wrong. So the specification that the first three items do not load on factor 2, do not have an estimated loading, is a hypothesis that I'm putting forth. And it doesn't mean that I'm saying that y1, y2, and y3 are unrelated to f2. It's that they're not related directly. They can still be related to f2 because f1 is related to f2. So if y1, y2, and y3 measure f1, and f1 is related to f2, then indirectly there's still a relationship. The zeros right here mean there's no direct relationship. And regardless of how many factors are in the story, each item still has only one error variance. And if someone asks you, hey, is that error variance, or is that unique variance, or is that specific variance? Your answer should be yes. Yes, it is. It's not the factor. That's what it is. We don't know what it is, but we know that it's not the factor. Everything left is E is up for grabs. So we will get unstandardized versions of each of these. We will get standardized versions of each of these. Typically, the standardized loadings are what we care about out of the standardized solution. Why is there 0 is a question. So the zeros for the loadings for F2 for the first three, and the zeros for the F1 loadings of the second set. Is that the question?
Yeah, I just don't understand. So if there is two factor, why I thought each factor should have their own loading. Like,
So if I were to allow loadings where the zeros are, that would turn this analysis from a confirmatory factor model to an exploratory factor model. And then I wouldn't be able to say as easily what is each factor. If all items measure everything, then it's much harder to try and figure out what that factor must represent. Here I am saying, no, the first three items only measure factor 1. That is my theory that I'm putting onto this data. And the second three items only measure factor 2. And so I can test the extent to which that is the case by fitting this model and seeing how well this model recreates the observed means, variances, and covariances of these item responses.
but if there is like a covariance or correlation between factors 1 and factor 2, then this doesn't work, right? Because if there is correlation, then how you know item 1, 2, 3 is only measuring factor 1? They must be somehow measuring factor 2 as well.
Yes, so the covariance or the correlation between these factors is not in the equations because covariances on their own don't directly predict item responses. But the covariances do show up in the matrix version of all of this, which is what we have to look at today. So the covariance does show up in predicting why items are related, but it only shows up in predicting the item relationships across factors. So items on different factors, the covariance comes into play then.
Okay, thank you.
Sure. Okay. So in terms of information that we have to work with to solve this puzzle as to what these item parameters should be and what the parameters that we've put up, there's a one-to-one correspondence between each aspect of the model. So the observed data going in are the item response means, variances, and covariances. Now that is the case regardless of whether you're using full information estimation or limited. Those are the pieces of data that are being used to solve the puzzle, essentially. So the role of the item intercepts is to recreate the item means. If you set up your model so that the factor scores have a mean of 0, the intercepts are the item means directly. Otherwise, they're conditional means at some other level of the factor. And so these will almost always be perfect. So long as each item gets a separately estimated intercept, those intercepts will fill in whatever gap needs to be there to recreate the item means. No problem. So that means we can't be wrong with respect to recreating the means. Likewise, the error variances for the individual items, so long as we allow one per item to be separate, they can't be wrong because they are going to fill in whatever part of the total variance is not the factor. So the same exact idea of y equals t plus e is at work here, except that we have a multiplier in front of t. So the total variability in each of these item responses is going to be partly due to the factor, and then e covers whatever's left. So it can change whatever the error variance is, to whatever value it needs to get back to the original item variance. So those won't be wrong either. Where the potential for disconfirmation or misfit or being wrong more broadly comes from is in the item factor loadings. Their job is to recreate the covariances among the items. And as long as you have fewer loadings than you have covariances to be recreated, you have the chance to be wrong. So really it boils down to the match between what the loadings say and what the covariances are. Everything else will work out okay as long as each item gets its own intercept, means are fine. Each item gets its own error variance, variances are fine. So then how does the model predict these things? Predict is not the right word. I'm trying to work on my terminology to make it clearer. The word predict, when I think about it, is like in a regression model, and I have my predictors and I have my outcome, right? And we talk about like how much of the variance do these predictors explain, right? And we can talk about that as a real thing. In this context, it's not really predict in that sense of the word, because what I can say is like, all right, of this item, how much of its variance is because of the factor? And I can say, okay, half of it. Well, great. Have I really predicted why some people answer higher or lower? No, I've just shoved that sort of conclusion up to the factor level. Oh, well, people answer higher because they have a higher factor score. Okay, why does this person have a higher factor score? I don't know. Like, I haven't really explained anything from a prediction standpoint. Really, what is the goal of this and what's happening under the hood, under the scene, behind the scenes, that's the metaphor I want, is that these parameters are trying to recreate the pattern of variance and covariance. They're not trying to say why some people are higher or lower on any of these item responses. It's not a why, because we're pushing the y up to the factor level and we still don't know why some people have higher factor scores than others. So the word that I'm trying to use here instead of predict is recreate. The loadings, intercepts, and error variances, as well as the factor, means, variances, and covariances, are trying to recreate the means, variances, and covariances of the original item responses. They're trying to replicate them. The extent to which they do a good job recreating them is the basis of model fit, means we are right about the structure. If they don't do a good enough job, then we have to figure out why we are wrong and change the model accordingly. So it's a recreation. Another analogy that might help with this. So for folks who are dealing with lots and lots of debt, a common response when someone knows that they have a lot of debts is to sort of bury their head in the sand and not open the envelopes and the bills when they come by, and they just sort of shove it in the closet and pretend like it's not a problem, right? Not talking from experience, but you know, it can happen, right? And so what's the first thing that if you go to like, you know, Susie Orman or a debt counselor or anyone will tell you to do? Figure out how much you owe, right? You got to open the envelopes, get organized, figure out how much you owe and to whom and at what interest rate. And then once you have the lay of the land as to what your debt actually is, how it's structured, then you can make the best decisions about what to pay first, what to pay next, how much should go to each thing. So the act of paying down your debt is the way I think of regression type modeling. Like, how much of my debt did this predictor account for? Okay, that's now I have this much left over. Great, that's R squared, that's prediction. This is more like, how much debt do I even have in the first place? How much debt is in this column versus that column versus that column? This is recreating like the pattern of the data. It's not trying to explain why people answered differently because we still don't really know. It's latent factor. We don't have the answer. Does that make sense at all? Maybe. It's a very different kind of like purpose than what every other class I teach is. Like, I'm usually trying to explain why y differs between people or occasions or whatever. We're not doing that yet. We're just trying to figure out what the responses have in common, and whether it's one thing in common, two things in common, whether our theory of how these items work is consistent with what the data say. Can our model recreate the item response, means, variances, and covariances? That's what we want to know. So I want to describe then how the recreation happens. Here are the rules. So using that same diagram where I've got the two factors, 3 items each underneath them, and each item measures only one factor or the other. The covariance between any items that are from the same factor. It's the loading of the one item times the variance of the factor times the loading of the other. So if you picture the path diagram, I'm going from one box up to the latent circle, down back to the second box. And the multiplication of those paths with the factor variance in the middle then gives me my model implied covariance between the two. If I work with the standardized solution instead, so the standardized solution converts all of the observed item responses into z-scores, mean 0, variance 1, as well as the factors into z-scores, then the standardized version of the loading is a correlation. It's a Pearson correlation. It goes from -1 to 1. So the correlation between the first box and the factor, the variance has to be 1 because we're in standardized, times the loading that gets from the circle down to the second box. That's what the model says. And I think I stuck, not soon enough. There we go. I know I stuck the picture in here again because I wanted that. So what I'm talking about is, how does the model predict the covariance between y1 and y3? Start at y1, pick up the path, pick up the variance of f1, come back down to y3. In the standardized version, it's the standardized path times 1 for the variance of the factor times the standardized path. So that's a pattern. Likewise, if I want to go across factors, so let's say I want y1 and y6, I start from the y1 box, I go up to factor 1, so I pick up this loading, then how am I going to get from factor 1 to factor 2? Looking for gestures here. Across the top, right? There's only one way to get there, over here. So I got to pick up the covariance, then I'm here, and then I come back down and pick up this loading to get to y6. So then the model says the covariance between y1 and y6 is whatever this number is times that number times that number. Now, what would happen if I took out this blue line? And then I said, what's the correlation between y1 and y6? I'd be like, cool, y1, up the line here to f1, uh-oh. If there's no blue line here, I'm done. So the model would say they're not related. So this factor covariance is the reason why items from different factors would be related to each other. The loadings then control the strength of that relationship within factors as well as across factors once you pick up the covariance. Back. There we go. That's where we were.
Lisa,
Yes, there.
can I ask you something in slide 17, please? Again, the diagram.
You want to see the diagram again?
Yes, please.
You know what? This is going to be, hang on. I'm going to get out of the big thing. That way I can flip around a little more readily. Hide this again. There we go. One second. It's thinking about it. There. Diagram. Yes. Question.
Yes, is if the factor loadings recreate the item covariances, why do we have different factor loadings for each item?
I missed the first part of the question.
If the factor loadings recreate the item covariances, the thing that we saw earlier, why do we have different item factor loadings within the same factor?
Okay. So question was, why do we have different loadings for each item within a factor if what they're trying to do is recreate the covariances of those sets of items? Is that the question?
Exactly. Yes. Yeah.
So if we made all of these loadings the same, that then implies all of the items are equal in their covariance with each other. Equally related to each other. Compound symmetry from the other class, otherwise known as a Roche model in IRT land. As it turns out, though, that is a plausible alternative model. So I could compare the fit of a model that has 3 separate loadings against another model where all 3 of these loadings are forced to be the same number. And I can test whether having 3 instead of 1 fits better. But if it's all one loading, then what you're saying is that the items are equally good at measuring this trait, which in turn means they should be equally correlated with each other. Equally covariate, excuse me. If I also forced their error variances to be the same, then it would be equal correlations with each other. So right now, what allowing different loadings is allowing you to say is, well, this item is less related to the other items because it's not as good at measuring the factor. That's why this item is less related than all the others. And that's a testable hypothesis based on how it relates to all of the others. But yes, those of you who've had IRT and learned about Roche models or one parameter models, that is a model in which all of the loadings for the items that measure the same factor are forced to be equal. It's an alternative. And because of that connection to what happens in IRT, that's one of the things I'll teach you how to do is to test whether these loadings are the same. A model that has equal loadings, that's called tau equivalent. Even though it should actually be lambda equivalent, that's not what we call it. Another case of bad labeling conventions. But tau equivalent models, equally discriminating. And, by the way, equal loadings is one of the assumptions that you make without testing when computing alpha. Alpha assumes equal loadings as well. Okay, did that answer your questions about the equal loadings?
Completely. Yes. Thank you,
Cool.
Lisa.
Other questions at this point? So the loadings and the covariance, those are doing the patterning. Those are creating the model recreated or model implied pattern of covariance that we then compare against the data and we see how far we're off. That's the big picture of this. The details can get to be a little bit tricky, which is why the big picture is helpful to keep in mind. So then items from different factors, as I said a little bit ago, it's the loading for the first item, the covariance to get across the 2 factors, and then the loading to get down from the second factor to the other item. That's how it works. And it would be the correlation version if you're talking about the standardized solution to recreate the correlations among items rather than the covariances. And the variability inherent in each item is going to be perfectly reproduced so long as each item gets its own error variance. So it's lambda squared times the variance of f, that gives you the t part, how much of that item variance is true, and then variance of e fills in whatever's left to get back to the right answer. Okay, now the way that you will see this in textbooks is going to look a little more like this. And unfortunately, in this case, we can't get away from the matrices. But my job is to make them a little bit less scary and useful. So in terms of what we're eventually going to be looking at in terms of model fit, the pattern created by the model versus what the original data say. We got this thing, capital sigma here. That stands for model implied variance covariance matrix. What does the model say the variances and covariances should look like given our factor structure? That is a function of, now we have capital lambda here, the loadings, multiplied by a matrix that holds the factor variances and covariances, multiplied by the same loadings transposed. So by the way, whenever you see this type of pattern of something times something and then the first thing is transposed, think squared. because that's what's happening here. Lambda squared times the variance of the factor. This is how it looks in matrix version. So we're squaring the loadings here. And then psi, which is one of the few Greek letters I know because this was the emblem for Psyche, is used to represent the matrix of error variances. So the pieces then look like this. This is the prediction that we get from the loadings multiplied by the factor variances and covariances. Then the loadings transpose so that everything is the right size, and then we add in the e's here. So those are the pieces that go into this thing. If I were to multiply this all out for you, which I did, much to my great chagrin, these sorts of slides, by the way, take like 3 hours to build. Like to get all the little numbers correct in all the little places and to have PowerPoint not crash while you're trying to render this giant thing is a miracle. So, can I get a shout out for putting a matrix in my slides? You know, those of you who've had me know that I don't do this very often because I just don't think this way. But this is one of the few cases where I think it does help, as much as I hate to say it. I think it helps. Because when I see something like this, I'm like, well, that's great, but what goes in each piece? Like, it's not very transparent. So this is the end result of this building process. So the first blue box here, items within factor 1 on slide 16. The diagonal. So where my mouse is right here. The variance of the first item is the first item's loading squared times the variance of the factor it measures. So that's T, essentially. That's true part. What is the contribution of the factor? Well, it's dictated by the loading. And we have to square the loading to make the math work. Then whatever is not addressed by the factor, E variance is the left, not the factor variance. So we have factor plus not the factor gets us back to the original variance of Y1. And the same thing is true if we go all the way along the diagonal. We have the loading for the second item times the factor it measures plus its error, the loading for the third item times the variance of the factor it measures, and then if we go down here where the items measure factor 2, it's the same except it's the variance of factor 2 instead of factor 1 because they're on a different factor. So that's the diagonal. It's contribution of the factor due to the loading plus whatever's left is error. Okay, with me so far? Maybe. They're like, I don't want to be with you, but I am. I don't like this. Now the off diagonals. So there's 2 different patterns here, and it depends on whether the items that you're looking at for their pair are from the same factor or not. So within factor 1, for instance, let's go right here. So row 2, column 1, that is the model predicted covariance between Y1 and Y2. Y1 and Y2 both measure the same factor, so they should be related. Otherwise, game over. So it's the loading of Y2 times the variance of the factor times the loading of Y1. Likewise, the loading of item 3 times the variance of the factor they have in common times the loading of item 1. So within that little block, what we are saying is that the relationships between the items are due only to the factor. Only. Another way of saying that is the assumption of local independence, meaning after we control for the factor, those covariances are assumed to be 0. The E's have no covariance. All of the reasons why Y was related is because of factor, and that's it. And that is shown explicitly in the zeros on this last matrix here. The E's are unrelated according to this model. So all of the reasons why items are related is because of factor, not because of E. So the same patterns hold then if we look at the items within factor 2. It's the loading of one item times the variance of the factor times the loading of the other item, and that gives us our pairwise covariance. Okay, with me so far on that? Maybe? Maybe? Questions?
Can I? It might be a dumb question, but like, why we have matrix? What does this equation do? Like, why we transform data in that way?
I can't hear you very well, but I think you asked why do we have latent factors?
No, I
Okay.
asked why we have this like a matrix equation, like what they do, why we transfer data in that way.
Ah, so you're not doing any of this. Let me just put that there. This is all happening for you by the program. The purpose of this slide is to show you how that factor model equation and the diagram, so all the parameters that are in that model, how they combine together to recreate the variance of each item and the covariances between the items. That's the purpose of this, is showing what is the prediction or what is the pattern that your item parameters and your factor parameters are making, and how does that translate into what the model says the relationships among the items should look like. It's factor variances, covariances, and loadings that are responsible for that, for predicting covariances.
But does the model, like if we use diagram and we put all the numbers in, does that diagram give us a clear idea?
I'm
Already.
sorry, I'm having a hard time hearing you. I'm trying to get my head closer to the speakers.
Is my microphone a little bit weird? Let me adjust it. Hi, can you hear me better now?
Yes, just speak slowly. It's blurry, it's not soft. That's my problem.
So I don't understand. We have a diagram, right? And
yes,
we can put all the loadings, all the variance, the number, the covariance into that diagram.
Yes.
Does that provide us a clear, like we already know each item's contribution, what is the covariant, what is the residual? So I just don't understand like what's this metrics can provide us, like.
I think the best way to say it is that the diagram is a shorthand way of representing the end result of the mathematical operations, and this is the end result.
Okay.
Okay. I can tell that you're not convinced, and I'm perfectly okay with that. Because what happens in practice, which I think you alluded to, is that, people will put the diagram in their paper. They will put the numbers, like what was the loading, what was the variance, and all that stuff onto the diagram. And that conveys the results of their model. So my purpose in trying to show you it this way is to foreshadow why it is that you can be wrong. How is it that CFA is a disconfirmable model? Because the statements that you're making in terms of what items load on what factors then translate into these patterns of covariance. So for instance, if I added, let's say that I added a loading from F2 to Y1. Well, then part of Y1's variance would be from F2, not just F1. But that would also have implications for how Y1 relates to the other items, because it would have an extra relationship to Y4, 5, and 6 that Y2 and Y3 won't have, because they don't have the cross loadings. Maybe I'm making it worse. It's entirely possible, but I'm trying. I will go down swinging. Unlike my illustrious softball career as a young person, I got called out on strikes more times than I care to admit, but I'm going down swinging now. I'm trying. So the things that people would do if they're wrong. You think you got it? Okay, well, thank you for humoring me, but I will tell you that we will get there eventually. This is a very different way of thinking about data and the purpose of an analysis than what we're used to, and I respect that that is a weird translation to make at first. So if you're wrong, right, let's say that this pattern that is implied by your model is off. That's going to happen. So let's say, for instance, that y1 and y2 are actually more related than what this pattern says. Then how would we fix it? Well, another way that we can say y1 and y2 are related would be to let their e's be related. So I could put a two-headed arrow between e1 and e2. And then the model implied covariance for y1 and y2 would be loading a y1 up to factor, loading back down to y2, plus the relationship between the e's. Likewise, if y1 was more related to y4, 5, and 6 than what the model predicted, one way to fix that would be to let y1 load on f2. And then that would be an extra relationship that is being captured by the model through what's known as a cross-loading, when something loads on something you didn't originally intend it, in addition to the one that you did intend. So knowing what the model says is the first step to knowing how you're wrong. And then how you're wrong dictates how you need to revise the model to become more right. More righter, as it were. All right, 249. Okay, other questions? Okay, so big picture. Loadings, their job is to recreate covariances. Intercepts are to recreate item means. Error variances for the items are to recreate the rest of the item variance that the factor wasn't getting. That's the big picture. Now we said at the top of class, right, what do we know about F1? It's imaginary. We think it exists. We hope that we've measured it with our items, but it's imaginary. We have to give it a scale for any of these numbers to be findable. That process of giving our F's a scale is known in part as model identification. There's actually two parts to model identification, and that's where we're headed next, I think. So I'm going to go back, zoom out again so that we can see a little bit better. So the first step is to create a scale. Because F is imaginary, we can't do anything with it until we have a way to figure out what its mean is going to be and what its variance is going to be. The second part of model identification is making sure that we have enough information across all of the items to actually solve for all of the parameters. And you need at least 3 items per factor to make this work without constraints. And we'll go through the math here momentarily. But the first part here is creating a scale. For those of you who have IRT terminology in your head, this is also called anchoring. It's the process of setting up what the mean and variance should be for any factor. So each factor has a mean, each factor has a variance, and they are separate because each factor is assumed to be normally distributed, and in the normal distribution, the mean and variance are 2 separate parameters that have nothing to do with each other. So the first step, give it a variance. You have 2 choices on this. One is to just say, well, the variance is this number, the end. And the most common version of that strategy is to say the variance is 1, so that essentially the variance looks like a z-score, or the factor looks like a z-score. Standard deviation is 1, variance is 1. Benefits to doing it this way is interpretability. If I think about what a loading is a slope. A slope is the change in y for a 1 unit difference in x. So a loading, in order to know what to do with it, we need to know what a unit of x is, or a unit of f. So if I say that f has a variance of 1, then I know that a 1 unit difference corresponds to a standard deviation difference between my different participants. It doesn't actually matter what the number is so long as it's greater than 0. You can make it a variance of 10, doesn't matter. 1 is just common. The downside of this approach is that it can cause problems with convergence once this factor is predicted by something else. So once a factor is predicted, rather than talking about its variance, we would talk about its leftover or residual variance. So the fact that we've nailed this down to one number can cause problems when that number needs to shrink because the factor variance has been explained by some other variable in the model. So we will start out this way because it's easier to interpret your model parameters if your factor is standardized. But towards the end of the course, we will switch to go the bottom way. Okay. With me so far? So if you want to give your factor a scale, option 1, make up its variance and say variance is 1. Boom, fix it. The other is to let it figure out what the variance must be in relation to one of the items. So the other choice here is to fix one of your item loadings to 1. The item that you have chosen to fix its loading is called a marker item. And it's not that you're saying that the item is perfect, because this is unstandardized. What happens is that the factor variance then becomes the reliable true score part of that item. So it's easier to think about it if it's a standardized loading. So let's say that you have a marker item whose unstandardized loading is 1, and that turns into a standardized loading of 0.9. If I square that 0.9, then I get the contribution of the factor. I need to know what the total variance is for the item. So the math works out such that 12.96 would be how much of the factor is due to that, how much of the item is due to that factor. So then the factor variance would be 12.96 because that's the amount of the total variance of the item that is due to the factor. It doesn't matter which item you pick. The only rule is that you have to pick an item that has a non-zero loading or it's not going to work and it will blow up. Question, Cassandra.
Hi. So one more time on the z-score factor, you said once a factor is predicted, the result is then the residual variance?
Yes.
Is that okay?
Yes. So where the first, hey, come back. Where the first strategy fails, or it can fail, is when that number that you said it's 1. Well, it's 1 if it's the variance of the factor, but if you want to have the factor then be predicted, that 1's got to shrink because it needs to become variance left over after the prediction. And so not having it fixed to a number and not being able to shrink, I've seen that cause model convergence problems before.
Okay, thank you.
Yeah, sure. So the thing that is difficult, I think, to understand at first is that this choice as to how to do this is completely arbitrary. What it boils down to is that in order to have your factor have a variance, something has to be 1. Either the factor variance is 1 and all the item loadings get estimated, or one of the item loadings is 1 and the factor variance gets estimated along with all the other loadings. Can I give you a real world example that might make this a little bit more palatable? Maybe? Okay, so story time. As a teenager and in college, I had a number of crappy jobs, as I'm sure many of you did. Hands up if you had a crappy job at some point in your life before this. Yeah, that's most of us. And some might say, oh, my crappy job is right now, but we're not talking about that yet. We're talking about the kind of job where you had to wear a name tag, probably work pants and work shoes, and make like $4 an hour, you know, flipping burgers, waiting tables, clearing dishes. What I did, most of it was waiting tables. I also worked at Walmart for a year in the shoe department. But I put myself through college waiting tables. And the place that I worked in college, which was actually one of my better crappy jobs, was a restaurant called Grisanti's. And Grisanti's was a local chain across Colorado and Nebraska. It has since closed, I believe, but it's basically an Olive Garden, if you've been to one of those. But rather than having unlimited salad and bread sticks, we had unlimited salad and bread loaves. But functionally, it was the same thing. And I worked there for 3 years or so, and one of the things that we did there was sing at people's birthdays. So when it was your birthday, you got a free dish of ice cream with some candles on it, and we all had to round up all the other servers and go to your table and sing. And the way that it worked, no one wanted to sing, by the way. It was like pulling teeth to get your coworkers to not go hide like somewhere when it was time to sing. But we all had to do it because invariably, eventually, you'd have a birthday and then you need to round up people, so it was like a goodwill gesture. So the way the song started, I'm holding the plate of ice cream in front of me here to give you the full visual, is that somebody had to first pick the key. And that person, whoever got their voice heard first, could control the song. So we go me, 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 like that, right? And when it was my turn, I did it that low. I go me, 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 because I have an alto voice who sings down here, as opposed to the girls that would be like me, 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 which is not a register that I have. And so we would do the song, happy birthday to you, hey, happy birthday to you, ho, happy birthday, dear so-and-so. And then people of the opposite sex would lean in and go, baby, happy birthday to you. And then we all clap. Okay, yes, I know, this is a true story. I did this like once a night at least. So my point in telling the story is this. All of the rest of the song not sounding like total crap hinged on the first person going me, 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 and the rest of us knew where to come into the happy birthday song. That's this. Okay? Setting the key is like picking the one. Because everybody knows how to sing happy birthday, you just need to know where to start from. The rest of the notes are all relative to that starting point. So you can play lots of songs in any key that you want. As long as you know what key you're in, everything is relative to that as a baseline. For those of you who are in marching band, right? Like there's somebody who's in charge of being like the middle person, and everybody lines up relative to that person, however many steps before, after, and the side. And then the formation works because everybody knows relative to something else where they should be. So this is all relative also. Something's got to be 1 is how this works. So if you say the factor variance is 1, that's fine. If all the loadings can be whatever, let's say that item 2 is much better than item 1. So item 2's loading might be 0.8 and item 1's loading might be 0.4. Cool. If I choose to do it the other way, where I make item 1 a loading of 1, then the loading of item 2 might become 1.4 instead of 1, because item 2 is better. So these numbers are not really numbers. They're all relative. It's just you're giving the scale an anchor point to start from as your variance. So it doesn't matter. Can we use the z-score factor method to determine which questions become the marker in the second method? You could, but it honestly doesn't matter. As long as you have an item with a non-zero loading, the model will fit equivalently. Because once you have your starting point, all of the parameters just line up relative to that. So you will see discussions about which should be the marker. It literally does not matter. You will get the exact same model fit. You will be just as right or just as wrong. The only situation in which it matters is if you have the misfortune to pick an item that literally doesn't measure the factor, because then there's no information to pass up from the item up to here because this loading is 0. That's the only thing that you can do wrong. Okay, with me? Yeah. Very happy I don't have to sing in my job anymore, except for on special occasions, in which case I break it out. And yes, I don't ever want to go to a restaurant and be sang to on my birthday ever again. I also had to sing at Shoney's, by the way, which is another defunct chain. Question: if we had different marker items, could we have the same standardized factor loadings for the 2 cases? Yes. Yes, exactly another reason it doesn't matter. The standardized solution will be literally the same regardless of how you set up this unstandardized solution. Because in the standardized solution, all items have variances of 1 and the factor has a variance of 1. And so then that's what 1 means in that context. So it doesn't matter. So long as you make sure that something is 1, either one of the loadings or the factor variance, you're good to go. Everything else will rearrange itself relative to that 1 as an anchor point. Okay. So that's one side of the model. The other thing we need to give the factor is a mean. Come on. That's on the next slide if it will go there. There's 2 choices for that too. Please? It's like, no, I broke my computer. It's mad at me. Well, I know what's on the next slide because I made it. So I'll just talk like I'm on the next slide 21. It's the factor mean. And it's the same set of ideas. Something got to be 0. Either you can say the factor mean is 0. Cool. That's what most people would do. That's the default in every program. Because then the item intercepts become the item means. Cool. Fine. You don't have to center it. Basically, you've centered the factor by making the mean 0. Or you restrict one of the intercepts of the items to be 0 instead, and then the factor mean becomes the mean of that item. So it's the same logic. The latter is far less common and only would be used in certain circumstances, probably in a longitudinal analysis where you're looking at change in factors over time. But the factor mean being 0 and the factor variance being 1 is all we need to set the scale for the factor, and every other model parameter will fall in line relative to that as a reference point. So, recapping, to scale a factor, something got to be 1, something got to be 0. All right, question, Nathan. Let's see if I can get to the next slide yet.
So what if, let's say that we're doing the z-score factor method and the questions don't have a whole lot of variation in their responses. So like there's no, let's say that everyone just responds super high, you know, like for measuring ability, they all place on the higher end. Then how one standard deviation isn't gonna mean, you know, it's not going to reflect like a very large amount of variation between people. So how would that show up in the model?
If an item does not have a lot of variability, then that will put a limit on how much covariability that it can have.
Okay.
And it might look like a bad item because it has a low loading.
Okay.
But that would be an instance in which I would want to be careful throwing it out. Because that item, if it's extreme, right? If everybody gets it right, or most people get it right, then that means it is an informative item with respect to measuring people of low ability. So
Okay.
I would not want to get rid of it for that reason, especially if I didn't have that many alternative items that are designed for measuring low abilities.
That makes sense.
Yeah, the intercepts generally don't enter the discussion in this framework because the slope is assumed linear. So if an item is good, it's assumed equally good for everybody. But that is an assumption and not a reality. Please? My thing is like, no. All right. It's not going to let me do it. Let me see if I can reopen it and see if it get any better. But if not, I know what the next slide is too. It's like it's a 2x2 grid, isn't it? Is that what's next on slide 22? It's like I made them. Maybe? That was one of the oddest compliments that I ever got after giving a talk, is someone said, "It was like you really knew what was on the next slide." Yeah. I wrote them. That seems kind of like a low bar. But it's all about what my computer is willing to do when Zoom and the screen capture is running. That's what we're at here. But it seems to be more cooperative at this point. So we did factor variance or item loading of 1. Then we have the alternative on the next slide. It's thinking it's on there. Yep, here we go. For the mean, either the factor mean is 0 or one of the intercepts is 0. Probably the one for the marker item if you go that way. And then slide 22, which I knew was coming, is this grid right here. So these are the choices of how you identify your factor by giving it a scale. It does not matter which quadrant you're in. What I like best, at least when we're starting out, is the top left quadrant. Factor mean 0, factor variance 1. Then the intercepts are the item means. It's as if I've centered my predictor already, and you know how much that pleases me to have centered predictors. And when I talk about what a loading does as a 1 unit change in X, I know what that means. It's 1 standard deviation in the factor. Cool. What is the default in every package that I'm aware of is the top right one. A marker item with respect to the loading, an estimated factor variance, but the factor mean is still 0 and all the intercepts are estimated. If you don't do anything special, that's what you get. The other combinations here I have listed for completeness, but I hardly ever see a free factor mean, because then it's just a little bit weird. It's not wrong, but it's weird. So in almost every case that we'll see, except for the ones where I'm literally just doing it to show you what would happen, the factor mean is going to be 0, and that's a default in all the programs. There. Of course, now it comes back just in time for me to basically end class. So after that, then we talk about fit and estimation and identification and how all those things fit together. But that's going to have to wait until next week. So, summary points from today. Very happy to have a job where I don't have to sing. Something gotta be 1. Factor variance or an item loading. Something gotta be 0. Factor mean or an intercept. Then play ball. All the other parameters will rearrange themselves relative to those numbers as an anchor point. Then our imaginary variable is less imaginary. All right, how are we doing? Yes. Also, the reason, by the way, that I don't have a standing desk is because part of the reason I went and got a PhD is that I never had to work a job where I had to stand all day again. I have earned the right to sit down. So that's what I do. Questions or things that you want to hear again or hear more about? Absolutely. That's a new one. I haven't seen the right on emoji. That's what I'm calling that one. No questions right now? Not right now. Fair enough. Coffee emoji. Yeah, I'm actually going unleaded today because I'm trying to sleep better, and cutting out the caffeine this late in the day is hopefully going to help with that. But we will see. It's an empirical question. All right, then if no one else has anything, I will sign off for now. I will say happy weekend to you. Let me know if you need anything. Office hours basically start now. I'm just going to stay logged on. So that's it for now. See you all next week. Thank you for being here.